Okay, in this second video, I'm going to move on to the second half of the review in which we practice solving trig equations. So just a quick reminder that most of our trig equations are going to have two or more answers, and that's pretty much or pretty well illustrated with this type of question here. When does sine of theta equal 1/2? Well, again, there are two positions on the unit circle where sine will be equal to 1/2. And that's ultimately what we really need to consider anytime that we solve one of these equations. So in number 18, we've got the equation 2 sine theta plus 4 equals 3. After we do a little bit of algebra to isolate the sine expression, we now know that sine of theta has to equal negative 1/2. And the only two positions where sine is equal to negative 1/2 in a unit circle are these two spots here, 7 pi over 6 and 11 pi over 6. If we were to use a calculator, even if it would produce an exact answer result, calculators only give us one result instead of two. And so part of the question structure on the test will require both or all solutions. For number 19, 4 cosine squared theta equals 3. Well, again, a little bit of algebra would allow us to get cosine by itself. Do keep in mind, however, that since we've got this cosine squared and ultimately a square root is necessary to isolate the cosine, we need to introduce the plus and minus symbol for the result, radical 3 over 2. And so the question becomes, where in the unit circle does cosine equal positive square root 3 over 2? And where does it equal negative square root 3 over 2? Well, that occurs in 4 positions inside the unit circle. We don't know which one would satisfy the original equation, so we've got to be prepared to produce all 4 of these results to the expression. Skipping ahead here to take a look at the multiple angles inside of a single trig expression. Remember my rule of thumb that I gave in class. Anytime you see a multiplier inside of the angle measure itself, that's kind of a giveaway that in order to find all of the solutions, we're going to have to take that many trips around the unit circle. So we might need 3 rounds or 3 trips around the unit circle in order to find all solutions. Let me try to explain why. If we were to replace 3 theta with a single angle measure, alpha, then the question becomes, in my green ink here, when does sine of alpha equal 1? Well, let's see here. Ignore this for just a second. Ignore that for just a second. Alpha would have to be 90 degrees. Or if we take another trip around the unit circle plus 360, then we'd have 450 degrees and then 810 degrees and so on. Well, we weren't trying to solve for alpha, we were trying to solve for theta. Now, 3 theta is equal to alpha, so 3 theta is equal to 90, 450, 810, and so on. And as we try to solve for theta, we must divide each of our answers by 3. Well, 90 divided by 3 is, of course, 30 degrees, and 450 divided by 3 is 150, and 810 divided by 3 is 270 degrees. Those 3 answers all exist within a unit circle, and so all 3 of these answers must be provided. If we were to add 361 more time, we would obtain an angle measure when divided by 3 would not exist inside of an initial unit circle. So I know that these 3 are going to be the solutions. Now, the problem was written with radians in mind, but you'll notice that I converted everything into degrees. My brain works a little bit better when we're rotating around the circle more than once with degrees. So I mentally converted to degrees for each of these results and then transitioned them back into radians for our final answer. You should be prepared on the test to answer in either degrees or radians as specified by the problem. I built this review on Math Excel, and I noticed that 23 is kind of beyond the scope of what I wanted to ask on the test tomorrow. So if you can handle 23, that's great, but don't expect a problem like it on the test. It's basically 1 1/4 rotations around the unit circle instead of an integer number of rotations. I'm stopping on 26 here because it involves one of our reciprocal functions, secant. Now, if we use the algebra to isolate secant, we end up seeing that secant theta has to equal -2. And that in and of itself is kind of a difficult expression for some students to solve. We're not that familiar with our reciprocal trig rules. So what might make it easier is reciprocating it. Instead of calling this secant, let's call it cosine. And if we reciprocate the left side of the equation, we should do so on the right. Instead of secant theta equals -2, we now have cosine theta equals -1/2. And when does cosine equal -1/2? Well, that happens in these two positions here, 2 pi over 3 and 4 pi over 3. Okay, and that brings us to a question that we do need a calculator to solve. In fact, it's instructed for us to use in the problem itself. Use a calculator to solve the equation on this interval. Now, what you have to keep in mind is that there are often more than one answer. There often is more than one answer in this interval, and we've got to be prepared and understand how to obtain both of them, even if the calculator gives us just one. When sine of theta is equal to 0.18, then of course we could use the inverse sine evaluated at 0.18 to obtain our angle measure. And our angle measure is 0.179 radians. By the way, our calculator needs to be set to radians to solve this problem because our instructions were given to us in radians. This is a radian measure. So if this is one of my answers, and by the way, 0.17 radians, that's somewhere over here. I don't know exactly where, but I do know that this is pi divided by 2, which is 1.5 something. So 0.17 has to be sitting over here somewhere in the first quadrant. Well, if that's the answer that the calculator gave me, there's another position that's got sine of the same value, and that's this side over here. So how do we obtain this angle measure on the left-hand side? Well, if this was a measurement in degrees, you might recognize that 180 degrees minus this angle measure would give us this angle measure. And that's exactly what we would do here in radians, except we're not using 180 degrees. We'll use pi radians minus our answer off the calculator, and we obtain the other result as well. So there are two results that satisfy this particular equation inside that range. Same thing with 29. Tangent inverse of 7 would allow us to find the theta value. So our calculator tells us that theta has to be 1.4289. Now again, 1.4289, that's somewhere in the first quadrant because, well, this position is half pi, which is 1.57, I think. So we're in the first quadrant. Well, how do we obtain the other angle measure directly opposite of that? Well, this time, the angle measure here is 1.42 radians, and the angle measure in this position is 1.42 radians beyond pi. So I chose to add pi to that to obtain the second answer. So it takes a little bit of creativity. Well, I don't know about creativity, but it takes a little bit of careful thought to establish the second answer. The first answer generated off the calculator isn't too bad, but then understanding your position around the unit circle, you have to do so carefully in obtaining the second result. A lot of these are very much the same, so I'm skipping ahead. And that brings us back to a couple more problems where we're solving an equation inside of a unit circle. Remember that some of these that look like quadratic expressions very easily can be solved using quadratic techniques. Now, I like to rewrite sine theta as the letter y, and in doing so, I've got the expression 7y squared minus 16y plus 9 equals 0. And I always think about factoring before I go to the quadratic formula. This is a non-standard trinomial, but it is factorable. and 7y minus 9 and y minus 1 are the two factors, which are good. What's interesting, though, is that when we solve this left side of the expression, we see that y has to be equal to 9 over 7. Well, that's not possible inside of a unit circle. The y values never exceed 1. So this left-hand factor does not produce a result to the trig problem. On the right-hand factor, we've got y minus 1. Well, that means that, or y minus 1 has to equal 0. So that means that y itself has to be 1. And where in the unit circle does y equal 1? Well, that exists at the position 90 degrees, or pi over 2. And that's the only answer to this particular question. Only real number answer to this question. Similarly with 35, I see this square here, and so I automatically think Pythagorean equation, or I'm also thinking, quadratic, can this be factored? And so I'm going to utilize a couple of those thoughts. I'm going to distribute the 12 to eliminate these parentheses, and then I'm going to utilize a Pythagorean identity to rewrite sine squared. And so after distributing and rewriting using the Pythagorean identity, I've got this expression in which all terms are written in terms of cosine. I'll move all of these terms from the right to the left, and again I get an expression equal to 0. I'll replace the cosines with an x, so x squared minus 12x plus 11 equals 0, and that's factorable. So my solutions exist where x is equal to 1, or when x is equal to 11. And again, x can't be equal to 11 inside of a unit circle, but x can be equal to 1 in a unit circle. That occurs at 0 degrees, or 0 radians. Again, the only real number answer for this particular equation. Now, the last example that I want to walk through here is number 37. Use a graphing utility to solve the equation. Let's just remind ourselves that this is, a technique that is available to us. If we graph the left side of the equation as a function and graph the right side of the equation as its own function, then we're going to look to see where those two functions intersect one another. Now, I used Desmos to create the picture, this screenshot here, and I captured it for note-taking purposes. The red curved line represents the left side of the function, and the blue straight line represents the right side of the function. And there are 2 points in which they intersect. The solution set, of course, then would be the x values 0 and 1.64. 0 and 1.64. Now, I don't anticipate allowing Desmos on the test or on the final exam, so you will need to use one of the TI calculators or your own graphing calculator. If you're having trouble graphing during the test or while studying for the test, by all means ask for some help, and I'll help you with the technical aspect of using those calculators. As long as you understand the process and the technique, that's what I'm after here, not necessarily your complete understanding of the technology. I'm skipping number 38 here because it was an interactive question on Math Excel, and it just didn't print out well. It didn't provide the parameters that I needed it to. So I'll drop that from this review and from the test. I hope these 2 videos helped you out, and again, pause and replay the video, listen to my comments. Hopefully that helps you better understand the process. And if you have any questions, then tomorrow morning during Flex, I'll be available. Also, before school starts, I'll be available to answer questions as well. Good luck.